has become the first country to return samples from the far side of the moon. The samples will be analysed in Beijing after the Chang'e 6 lunar module landed in China's northern Inner Mongolia region.
For centuries, the moon only ever showed us one face. The other half remained hidden, cloaked by orbital mechanics, unreachable and unseen. But China has just uncovered the other half of the moon, revealing a different world than we could have predicted.
Chang'e 4 lunar probe has just landed on the far side of the moon. But this is the first ever landing by any country on that side of the moon.
Their Chang'e 6 mission brought back actual pieces of the moon's invisible face. For years, planetary scientists debated why the moon's two hemispheres looked so different. Now, with this single sample return, we have the answer in our hands. The hidden side. For thousands of years, Earth's view of the moon never changed. Night after night, the same features greeted human eyes. But all that time, the other side of the moon remained completely hidden from view. The moon is tidally locked to Earth. That means the time it takes to rotate once on its axis is exactly the same as the time it takes to orbit Earth. Because of this perfect balance, we only ever see one hemisphere. The far side never turns to face us, no matter how long we watch. Humanity's first actual glimpse of that hidden hemisphere came in the year 1959. The Luna 3 probe looped behind the moon and sent back the first photographs ever taken of the far side. The images were low resolution and grainy, but they were groundbreaking. The far side appeared far rougher than expected. It was covered in a thick patchwork of impact craters and missing most of the dark basaltic plains that dominate the near side. That difference in surface texture was the first clue that the moon might not be geologically uniform. But blurry photographs could only hint at what was there. The real questions remained unanswered. What was this landscape made of? No one could answer that without physical samples, and getting those samples was a bigger challenge than anyone imagined. Why was the far side such a difficult target? The answer lies in the moon's own mass. Any spacecraft that lands on the far side is instantly cut off from Earth. Radio waves, the way we send and receive data, cannot travel through the solid rock of the moon's body. If you land a rover or a lander on the far side, you lose contact the moment it touches down. For years, that communication blackout stopped every serious attempt to explore the far side. We could map it from orbit. We could take better and better photographs. But no one had landed there. No one had touched its soil. And certainly, no one had brought any of it back to Earth. That all changed when China launched its Chang'e missions. These were precision-engineered steps towards solving the far side problem once and for all. Instead of avoiding the blackout, China built a bridge across it. And that bridge is what finally made the far side real. Now, after decades of speculation and theory, they finally have the proof. The moon's hidden face. The sample that came back has begun to reveal answers to questions we have asked for over 50 years. What we are learning from it is rewriting the moon's history and forcing us to rethink how planetary bodies evolve after cosmic violence. China's bridge to the far side. There was one simple reason why the far side of the moon stayed untouched for so long. You could not talk to it. The moon itself blocked the signal. Any lander or rover placed there would fall silent the moment it touched the surface. And in space exploration, silence is the most dangerous thing imaginable. No matter how advanced the hardware or precise the landing, a blackout meant loss of control. You could not adjust instruments. You could not see what the rover saw. You could not even confirm whether the mission survived impact. For decades, that risk was considered too high. But China decided to solve the problem. In early 2018, the China National Space Administration launched something no one else had seriously attempted: a communication satellite specifically built to talk to the far side. They called it Queqiao, which means magpie bridge in Chinese folklore, a reference to a story where a bridge of birds connects two separated lovers once a year. It was a poetic name for a purely practical mission, and it worked. Queqiao was not sent into a simple orbit around Earth or even around the Moon. Instead, Chinese engineers placed it in a gravitational sweet spot known as the Earth-Moon Lagrange Point 2. This point sits far beyond the Moon, on the opposite side from Earth. It is one of several positions in space where gravitational forces and orbital motion balance out. At Lagrange Point 2, an object can stay relatively stable without constantly burning fuel to adjust its position. From that spot, Queqiao has an uninterrupted line of sight to both Earth and the far side of the Moon. That made it the perfect relay. Instead of trying to punch signals directly through the Moon, Queqiao simply bounced them around it. This setup transformed a decades-old limitation into an operational advantage. Now, landers could be guided in real time as they descended onto the far side. Data could be streamed back to Earth. High-resolution images, spectrometer readings, radar scans, all of it could move across that invisible arc from the Moon to the relay and finally back to mission control. This achievement was not just about the Moon. It was also a demonstration of something bigger. China had shown that it could build deep space infrastructure. When Queqiao was in place and functioning, it allowed for the next step, the Chang'e 4 mission.
In most aspects, the Chang'e 4 is a twins with Chang'e 3. Yeah, Chang'e 4 will land on the far side of the Moon.
That lander and the Yutu-2 rover it carried would be the first spacecraft in human history to perform a soft landing on the far side of the Moon. But without Queqiao, it never would have been approved. The bridge had to come first. Queqiao's success also unlocked a new way of thinking about space. Instead of relying on single-shot missions, China was building an interconnected system. The satellite, the lander, the rover, and the ground stations all functioned as one machine, stitched together across 250,000 miles of space. And that machine had one job: reach the side of the Moon no one had ever touched and listen. The data that came back from that first landing in 2019 was extraordinary. But more important than what was found was the fact that anything could be found at all. The silence was finally broken. The hidden side of the Moon was no longer mute, and once communication became possible, the rest could follow. And yet, communication was only the beginning. Landing a rover was a proof of concept. But what scientists really wanted was something no satellite or camera could deliver. They wanted to hold the Moon's buried secrets in their own hands. They wanted to bring the far side home. The moment the Chang'e 4 lander touched down on the far side of the Moon, the rules of lunar exploration changed. For the first time in human history, a working machine was operating on ground no one had ever physically accessed. It was not a simulation. It was not a flyby. It was a controlled descent into the deepest scars of the Moon's past. The chosen landing site was not random. China selected the von Karman crater, a massive impact zone located inside something even more significant: the South Pole, Aitken Basin. This was one of the oldest, deepest, and largest impact structures in the entire solar system. At more than 2,400 kilometers wide and over 13 kilometers deep, it represents a direct excavation into the ancient Moon. This basin matters because of how impacts work. When something hits a planetary body with enough force, it does not just create a surface dent. It cracks through the crust and may even throw up material from the deeper layers below. The South Pole Aitken Basin was formed more than 4 billion years ago by such a catastrophic event. Scientists believe that the impact was so violent, it may have exposed pieces of the Moon's mantle. That possibility made the site priceless. No Apollo mission, no robotic lander, and no Earth-based telescope could access mantle material directly. Only a basin of this magnitude could have pulled it to the surface. The chance to study ancient, untouched layers of the Moon made the Chang'e 4 mission more than a milestone. It made it a breakthrough in planetary science. Once on the ground, the mission deployed its key instrument, the Yutu-2 rover. The rover, whose name means Jade Rabbit, was designed not just to survive the harsh environment, but to analyze the ground beneath its wheels with cutting-edge tools. Yutu-2 carried a visible and near-infrared imaging spectrometer. This device allowed it to analyze the mineral composition of lunar soil by studying how it reflected light across various wavelengths. What it found surprised even the mission planners. Instead of the typical near-side basalts, lava rocks rich in iron and titanium, the far-side samples showed high concentrations of low-calcium pyroxene and olivine. These minerals are not usually found near the surface. They are born deep in the mantle, formed under immense pressure and heat. Finding these minerals confirmed that the impact event at the South Pole Aitken Basin had indeed exposed the deeper interior of the Moon. This was not just surface regolith. This was mantle material, sitting on the surface and waiting to be analyzed. But that was only part of the discovery. U-22 also carried a ground-penetrating radar system. This radar allowed it to peer below the surface, sending signals down through the regolith and measuring how they bounced back. What the radar revealed was a layered history far more complex than expected. The subsurface was not uniform. Instead, it was a stack of different geological layers, some formed by lava flows, others by impact ejecta, and many mixed with fragments of ancient rock. These layers extended tens of meters below the surface. Some were packed tightly, others loosely bound. Each layer was a snapshot of lunar history, recording eruptions, collisions, and erosion going back billions of years. The deeper the radar looked, the more it confirmed the theory. This site was not just a random patch of gray dust. It was a natural drill core, created by violence, preserved by silence, and finally revealed by robotics. But while spectroscopy and radar provided strong clues, they could only go so far. They could not place the samples under a microscope. Only a physical sample return could do that. The Chang'e 4 mission showed that reaching the far side was possible, but it left one massive question open. What exactly are those minerals made of? And what do they tell us about the Moon's birth? That answer would come from a small metal container launched from the Moon's surface and flown back to Earth. Inside it would be dust and rock that had not been touched since the early days of the solar system. And what that container revealed when it was finally opened would change everything. Unpacking the dust. When the Chang'e 6 return capsule parachuted down into the deserts of Inner Mongolia in 2024, it carried a payload smaller than a shoebox. Inside that box was the first lunar soil ever collected from the far side of the Moon. It was not flashy, it was not visibly alien. But in the world of planetary science, it was more valuable than gold. That box contained something we had never touched before. The chemistry of a place no human had ever seen in person. As scientists opened the sample container, the first observation was immediate and visual. The soil was different. It did not resemble the fine, dry, powdery dust collected by the Apollo astronauts on the near side. It was lumpier. It clumped together in heavier chunks. Some described it as stickier, almost like damp flour, though of course it contained no moisture. Others noticed that it had a higher density of bright mineral fragments, pieces that sparkled under lab light and reflected a different geological history than any previous sample. This was texture suggested that the mechanical properties of the regolith on the far side had evolved under different environmental pressures, impact patterns, and perhaps internal heat conditions. For example, where near-side dust flowed like dry snow, this far-side dust resisted movement. Any future mission to build on the Moon's far side must account for this. Wheels will behave differently. Drills will face more friction. Structures might need heavier anchoring systems. It is not just another location. It is another engineering environment entirely. But the real story came not from what the sample looked like, but from what it was made of. Chinese scientists quickly began analyzing the mineral composition of the soil. They were looking for two main things: volcanic origin and crystallization temperature. These factors tell a geologist how hot the lava was when it erupted, how long it took to cool, and what layer of the Moon's interior it likely came from. The Chang'e 6 soil came from a volcanic plain, not unlike those seen on the near side. But the composition was not the same. Using thermal analysis and mineral thermometry, the team discovered that the lava which formed these far-side basalts had crystallized at around 2,000 degrees Fahrenheit. In comparison, similar lavas from the near side had crystallized at temperatures closer to 2,200 degrees Fahrenheit. In other words, the Chang'e 6 sample did not just confirm that the Moon has two faces. It told us why those faces are different. The far side has a colder history. It had fewer internal heat sources. Its crust is thicker, older, and more resistant to melting. This is why the far side is more heavily cratered. It did not resurface itself with lava nearly as often. One mineral finding supported this even further. The sample had a notably high content of anorthosite fragments, a kind of rock associated with the Moon's primordial crust, especially the highland regions. This meant the regolith in that location was constantly mixed by ancient impacts, pulling in older material from the surrounding hills. So even though the lander touched down on a volcanic plain, it scooped up a cross-section of lunar history. This was critical because it allowed scientists to examine the blending of crust and lava across geologic time. It gave them a timeline, not just a chemical profile. The more they studied it, the clearer it became. The far side had experienced far less volcanic recycling. It had cooled faster and evolved differently. That evolution confirmed what many had long suspected. The Moon is not a uniform body with random variation. It is a split world, shaped by asymmetric heat distribution, unequal radioactive decay, and a legacy of giant impacts. The Chang'e 6 sample return mission finally handed planetary scientists the missing key to a locked room. And behind that door was a blueprint of how the Moon cooled, how it cracked, and how its inner workings froze into place. But the implications go even further than the Moon itself. Because this thermal imbalance, this split personality, may trace back to the Moon's earliest moments, down to the moment it was born. And the data now in China's laboratories might finally confirm one of the most important theories in all of planetary science, that the Moon was not formed peacefully, but in the firestorm of a planetary collision. A new look at lunar water. For most of the 20th century, scientists believed the Moon was completely dry. That belief held firm through the Apollo era. The rocks brought back by astronauts showed no trace of moisture, no signs of water locked in the minerals, and certainly no pools of ice beneath the dust. Every theory was built on the assumption that the Moon had been baked dry by the violent heat of its formation. But in recent years, that assumption has cracked open. The first major shift came from orbiters. Instruments aboard probes like India's Chandrayaan-1 and NASA's Lunar Reconnaissance Orbiter began to detect hints of hydrogen at the poles. These findings suggested that water ice might exist in the permanently shadowed regions, places that have never seen sunlight in billions of years. The poles quickly became the new frontier, and space agencies worldwide shifted their attention toward those cold, dark craters. But then China's Chang'e missions added a new piece to the puzzle. The Chang'e 5 mission, which landed on a sunlit plain in the northern Oceanus Procellarum region, brought back samples that told a different story. These rocks were not gathered from cold, shaded craters. They were scooped from an area bathed in sunlight. And yet, inside those sunlit grains, scientists discovered something completely unexpected: chemically bound molecular water. The team found a new phosphate mineral named Chang'e and another substance nicknamed ULM1, short for Unknown Lunar Mineral 1. ULM1 turned out to be a hydrated salt, a magnesium chloride compound that held actual H2O molecules in its structure. Even more surprisingly, this mineral also contained ammonia, which is often a chemical marker associated with volatile delivery by comets or early solar system chemistry. This discovery changed the definition of lunar water. It was no longer limited to frost or ice. It existed in complex chemical bonds within rocks that had been exposed to sunlight for millions of years. The Moon, it turned out, has multiple water cycles. Some of it likely arrives via solar wind, interacting with oxygen in the soil to form hydroxyl. Some may be native, remnants of water-bearing minerals from the Moon's early history. and some may be chemically stable even in harsh conditions, locked inside salts and released only at high temperatures. What makes this finding even more significant is its location. If water exists in sunlit regions, then resource extraction becomes much easier. No longer would missions be limited to dark, hard-to-reach craters. Instead, robots or astronauts could mine water from hydrated minerals across wide areas of the Moon, using heat or chemical reactions to extract it. This kind of water is harder to detect with orbital sensors, but it is far more valuable. It is stable, it is portable, and it exists outside the poles. That rewrites mission planning, equipment design, and long-term goals. It also shows that lunar water is more common and more complicated than we ever thought. China's discovery has put them in a strong position. While NASA focuses on ice at the poles, China is mapping water chemistry across sunlit terrains. The data from Chang'e 5, combined with the regolith from Chang'e 6, offers a layered view of how water moves, hides, and evolves on the Moon. It suggests that the far side, like the near side, may contain multiple water types, even if its chemistry is colder, older, and less volcanic. It also raises a deeper question. If the Moon contains chemically bound water in minerals, could other airless bodies like Mercury, certain asteroids, or even Mars's moons contain the same thing? The implications stretch far beyond the Moon. They affect how we search for water, how we define habitable environments, and how we plan to extract resources for future missions deeper into space. Because just as water exists where we once thought it could not, the next major discovery might be buried deeper still. And what China is planning to do next could bring that secret to the surface. The future of lunar exploration. What China delivered back to Earth is not just a snapshot of the past. It is a preview of the future, and that future is already underway. The far side regolith, as revealed by the samples, behaves nothing like the near side dust we have known for decades. It is lumpier, heavier, and filled with fractured mineral chips that likely originated from deep crustal layers. This composition means future missions must prepare for dramatically different terrain. Wheels that worked well on the near side might clog or slip on the far side. Drilling rigs will need stronger torque and sharper bits. Habitat construction, especially those using regolith as shielding, may require customized machinery. You cannot treat the far side of the Moon like a mirror image of the near side. You must respect it as its own environment, an uncharted domain with its own rules. That is why Chang'e 7 and Chang'e 8 are so important. These two missions will not just observe or analyze, they will test infrastructure. Chang'e 7 is planned to target the South Pole, the same region that NASA's Artemis program has prioritized. Chang'e 8 will go even further. This mission aims to begin the first field experiments in lunar resource utilization. That includes testing how to extract oxygen from regolith, how to print structures using in-situ materials, and how to power systems with lunar solar energy. It will serve as a prototype for long-term operations. China has openly stated that its endgame is a permanent international lunar research station by the mid-2030s, with partners already being recruited. What makes these plans even more important is China's decision to share the far side samples internationally. While most countries guard their space data tightly, China has offered limited access to these materials through global science partnerships. Already, scientists from France, Russia, and Pakistan have begun collaborating on joint lunar studies. This positions China not only as a lunar explorer, but as a scientific broker, a gatekeeper to one of the most valuable data sets in planetary science. The Chang'e missions have already altered the timeline. Before Chang'e 4, no one had landed on the far side. Before Kachao, no one had maintained continuous communication with that region. Before Chang'e 6, no one had physically touched far side regolith. Now, all of that has changed. And the path to the Moon no longer leads to one destination. It splits. One path leads to the near side, a familiar terrain mapped by Apollo astronauts and robotic landers. The other now leads to the far side, a colder, older, less forgiving world where the rules are different and the stakes are higher. And somewhere between those two paths lies the future of space itself. In that sense, the far side of the moon is not just a place. It is a test to see if we are ready to operate beyond the reach of Earth, beyond constant sunlight, and beyond the familiar. Thanks for watching. See you in the next one.